We have a talk about automated analysis and synthesis of message authentication codes. That's my personal research field. And for today, oh, that doesn't work. Now it works. And first I will give a short intuition about what message authentication codes, or short MACs, are. And then I will talk about the relevance of MACs for the 6G project. After that I will give us short idea, a very high level idea of our approach and methodology. And in the end I give a short showcase of our results. But let's start with the intuition for MACs. MACs is a small digital tag which is normally linked to a message, and when you send a message over a network, for example via the internet, you just compute the tag for a message and send it with you. Why should we do it in the first place? Because if we want to ensure goals like the integrity or the authenticity of a message, we need to do it somehow, and message authentication codes are the primitive we use in cryptography. We have a symmetric cryptographic primitive, which is in the sense of MACs the co-part to signatures in the asymmetric part, and normally we compute the MACs using a pseudorandom function keyed with the symmetric key. And in practice we have, for example, CBC MAC, which is not secure in all cases, but the most easy one I think most of you may know. Then we have HMAC, which is very efficient, and we also have parallel MACs like LightMAC or PMAC. To be a bit more specific, more mathematic, a message authentication code scheme consists of 3 algorithms. We have a key generation algorithm like most cryptographic schemes. In our work, in our methodology, we don't really care about the key generation, we just assume it is there and it is secure. Then we have a message authentication code scheme which produces the secure tag. And in the end we also want to verify whether the tag is secure and everything went well or it did not went well, which is why we have a verification algorithm. The verification algorithm takes the message and the tag and then says yes or no. We also want that our schemes are correct, so if we compute a MAC, we also want that the verification of our tag and message is correct. We use canonical verification since we just recompute our MACs here. And for security, we consider a very strong security definition, the strong existential unforgeability experiment, which when you look in the oracle of the security experiment, we don't only want to have forgeries for messages, but also message and tag pairs. So an adversary may also use an existing tag for different messages, which is just one of the strongest security definitions there are for message authentication code schemes. Okay, and our relevance for 6G, let's talk about that. Of course, symmetric key schemes are generally faster than asymmetric ones, which is good for a lot of environments like where you have restricted hardware or IoT devices or mobile devices, which is a very big point in confidential 6G. And we also have good scalability because we can just increase the network without much overhead from our primitive. On the security hand, we have data integrity and authentication, and this can enforce secure communication in our 6G networks. And because we have a symmetric key primitive, we are also mostly resistant to post-quantum attacks, which is also pretty nice since the standardizations from NIST are mainly very inefficient compared to the existing algorithms. So this is a big plus for our message authentication codes. And for the pillars you already saw in the other talks, we are generally considering the cryptographic pillar, since I'm at a cryptographic chair. Well, then let's start talking about our methodology. I was studying for the last years now. So our goal is we want to automatically generate message authentication code schemes and also analyze their security. And how do we do it? Or why do we do it in the first place? The whole field of message and authentication code schemes is pretty well studied. So our goal was to maybe find new schemes that were not considered yet, but also get a better understanding and find alternatives for the existing ones. And we had a lot of challenges there because for our schemes, when we want to automatically generate them, we also have to consider variable length. So we don't have a fixed environment where we can look at all schemes, but we have infinite many schemes to consider. On the other hand, we want to cover all common schemes because it is a well-studied field. We also want an efficient algorithm to analyze and generate our schemes. Otherwise, we cannot compute our results, and we want as few constraints as possible. So how did we do it? In the first place, we represent max with direct acyclic graphs. And the nodes in our graphs are simply the computations we want our Mac to perform. So here are some of the nodes we consider, for example, a pseudorandom function or the input message blocks and XORMOX. So very basic computational blocks, and we consider most of them. And then when we have our direct acyclic graph and our set of nodes, we can simply just make a permutation over all existing graphs with the constraint of being direct and acyclic, and then we can generate our message authentication code schemes automatically. And it looks like this. So on the left we have, I would say, normal or standard abstraction of a message authentication code scheme. It's the eCVC MAC, and on the right you can see how it would look like within our framework being a direct acyclic graph. We also have a modular variant for the initialization part, the iteration part, and the finalization, because the most interesting parts are the iteration graphs, because they mainly compute most parts of the message, and we want to look at them. So this was the part where we generated our schemes, but we also want to prove the security of our schemes. So we created a type system for our graph, and the type system holds the properties we want for our graph, or we want to consider while analyzing our graph. And we have like 4 main property parts. It's type, which assigns the properties to a single node. Then we have dist, which relates 2 nodes in our graph for all nodes in the graph. Then we also need a type for keys, because we have multiple pseudorandom functions and we want to test whether they are independent or not and how they influence each other. And last but not least, we have length, which just stores the length of our messages within the graph. We need the last part because we have nodes like the concatenation, which may increase the sizes of our messages, and so we need to ensure the correctness of our construction. Good, and we use a type interference system to map those properties from our type system upon a graph. And we do it by starting with nodes without any parent nodes, like the input message node block or a counter node block. And then, based on axiomatically defined properties of those 2 nodes, we just start inferring the rest of the graph with the properties we have. We analyzed every possible case that could happen, so our proof should be correct, then our graphs in the end and the properties we did are also correct. And if the last block we have has pseudorandom function properties, then our whole graph we created and analyzed is a secure message authentication code scheme. Okay, and we implemented all of that. It was quite a lot of code, like 3,000 lines of code, and we made it run. And here are some of our results. So on the left you can see how many nodes did we consider for a graph, so what is the size of our graphs, and how many differently keyed pseudorandom functions did we consider, and then you can see how the numbers get bigger with the amount of nodes, and how many graphs we created, secure graphs, are on the left. And on the right we also considered which of those are parallelizable. So those you can see on the right for each column. Exactly, it was quite a lot. Here are two. On the left you can see CBC MAC again. And on the right we have one graph which is pretty similar to CBC MAC, which has an additional pseudorandom function block. And I just wanted to showcase you that a lot of schemes we found are simply inefficient. So they create new nodes somewhere which don't provide any additional security or any additional properties that are desirable, and just make the whole computation less efficient. But that's not all we have. We also created interesting new ones with, on the one hand, comparable efficiency to existing schemes, but also on the other hand with interesting new properties or properties to consider. And we implemented two of those schemes and tried to compare the performance of our schemes with existing ones, and we see that they in some cases are, or not in some cases, but in general are comparable to the existing ones. So we have found alternative schemes, but on the other side here are parallel schemes may also be slightly more efficient than existing ones, because especially regarding parallelability in computation, it really depends on the setup you are using and the hardware, where one can be fast and the other can be less fast. Okay, thank you for your attention.